Hi, I'm Alan, and today I shall present our work, Telescope, a novel approach to perform memory access telemetry for applications with gargantuan memory footprints. This work was done while I was interning at Intel Labs, Bengaluru. But first, some background. Applications with memory requirements of the order of terabytes are becoming increasingly common in the data center. This trend is fueled by various domains such as large language models, large in-memory databases, and various use cases in high-performance computing. A key enabler of this trend is the emergence of tiered memory systems. In a tiered memory system, memory is presented in tiers where each tier is composed of different hardware with different properties. Broadly, there are hot tiers, which are placed closer to the processor and offer low capacity memory at low latency and high bandwidth. And then there are cold tiers, which are farther away from the processor and offer high capacities at high latency and low bandwidth. However, a tiered memory system provides benefits only if the data is placed accordingly in the various tiers. We need the frequently accessed data or hot data to be placed in the hot tier. Conversely, the cold data must be placed in the cold tier. Optimal data placement into tiers requires telemetry. Here we define telemetry as the monitoring of memory access patterns of a workload. The telemetry helps us identify the hot and cold parts of a workload's memory footprint. And once identified, the hot data may be placed in the hot tier, while the cold data is placed in the cold tier. And if everything goes well, the workload experiences, majority of the times, hot tiers access latency and bandwidth, and the cold tiers capacity. So effectively, the workload gets to enjoy the best of both worlds, giving maximum performance on the system. However, this is feasible only if the telemetry is good enough. Ideally, the telemetry should identify hot and cold data precisely, that is, at fine granularity, ideally at the page size used by the application. It should be able to do that fast, and it should stay fast even as the memory footprint scales to the order of terabytes. Finally, the performance overheads of this telemetry must be minimal. Prior approaches that do telemetry fall into three broad categories: linear scanning of page table entries, region-based sampling, and using performance monitoring unit counters. Let's look at these one by one. In memory, each page is indexed by a page table entry. Each page table entry contains a physical page frame number, which on extending is the physical address of the indexed page. Alongside the page frame number, there are some status bits that carry some metadata related to the page. Among these, the accessed bit is of key interest to us. This bit generally indicates whether the page was accessed since it was mapped. When a page is first mapped, this bit is 0. Later, when the CPU accesses an address in that page, it first translates the virtual address to the physical address. The translation is searched for in the TLB, and if it is not found there, a page table walk ensues. During the course of this page table walk, the page table entry is accessed by a hardware page table walker. The page frame number is read to get the required physical address. When this is done, the page table walker updates the accessed bit in the entry to 1. Linear scanning of page table entries is done on a thread running beside the target workload, generally on another core. This thread is put to sleep so as to not hog too many resources and wakes up every 1 millisecond or so. On waking up, it linearly scans through all the page table entries corresponding to the target workload and checks which entries have accessed bit equal to 1. These pages are the ones that were accessed in the last millisecond. In the figure shown, those pages are highlighted in green along with their corresponding page table entries. Then this thread also resets the access bit to 0 in every entry it scans during the first scan itself. And this enables it to catch accesses over the next millisecond. Several Linux kernel algorithms for page management, such as KSTLD and MGLRU, they rely on this approach. The problem with linear scanning, though, is scalability. As memory footprints approach terabytes of base pages, one full scan can take over a minute. The workload access pattern may not be stable over such a long interval. Therefore, we need a different approach when we're dealing with terabyte scale memory. The second approach, region-based sampling, makes linear scanning faster by reducing the number of PTEs to be scanned. The workload's mapped address space is divided into regions. One page table entry is randomly sampled from each region. The accesses to this page table entry are taken to represent accesses to the entire region. Every 1 millisecond, the thread awakes and identifies which pages were accessed, and every region maintains an access count. If the sampled page table entry of a region was accessed, then its access count is incremented. Finally, this process repeats itself and a new page table entry is picked every round. Every 100 milliseconds or so, region boundaries are updated. Regions are split into subregions to improve precision, while adjacent regions with identical access patterns are merged to keep the region count under check. The successive split and merge paradigm ensures that regions converge to the underlying access pattern over time. The most well-known tool that operates on this approach is daemon, or the Data Access Monitor, which is now a part of the Linux kernel. The limitation is that we find region-based sampling to fail at the terabyte scale. As the number of pages per region grows, the probability that a sampled page is indicative of the entire region it is in, it becomes lower. We find that for a workload with a 10 GB hot data in a 1 terabyte working set, daemon detects nothing in 1 minute. The final approach involves collecting samples from performance monitoring registers present on some architectures. These can be used to collect memory access event samples which contain the data address of the event. The problem with this approach, aside from being restricted to some architectures, is that the overheads are quite high. Recording the samples to memory is triggered by an interrupt. Repeated interrupt handling slows down the target workload. For a large memory footprint, we will need a high sampling rate to collect enough samples for accurate profiling, and that implies more frequent interrupts and therefore a higher degree of slowdown. Now I shall present our work, Telescope, and show how its design enables effective memory access telemetry at the terabyte scale. Telescope exploits the radix tree structure of the page table. Radix tree is a multi-level tree data structure that is used to maintain the page table on most architectures. On 64-bit x86 machines, there can be 4 or 5 levels to this page table. On this slide, we see a 4-level page table. The page size is 4 kilobytes and the page table entries are 8 bytes each. So at each level, there is a page table page that contains 512 page table entries each. To walk the page table, a 48-bit virtual address is split into 4 9-bit chunks and one final 12-bit chunk. This concept is illustrated here with the help of 3 example virtual address translations. Each of these 9-bit chunks is used to index into the correct entry at each level of the page table. And then finally, the remaining 12-bit chunk is treated as byte offset within the physical page. In the page table walk that we just saw, the page table walker sets the accessed bit to 1, not just at the last level of the page table, but at every level. The corollary is that if the access bit is 0 at a higher level page table entry, then all the lower page table entries beneath it will have access bit set to 0 as well. So by checking the accessed bit at a higher level, we can detect access patterns faster by an order of magnitude, but the precision or the spatial granularity of detection falls by an order of magnitude. Telescope augments region-based sampling with this insight. Access tracking at a higher page table level is used for coarse-grained convergence, while access tracking at a lower level enables fine granular convergence. So how does Telescope decide which level of the page table to profile on, which means to sample accessed bits on? Here in this example, we have two regions. We see the three lowest levels of the page table relevant to these regions as well. For simplicity, we assume four page table entries at each level rather than the conventional 512. The lowest level page table entries are colored to indicate the region they belong to. At the two higher levels, a page table entry is colored with the region's color only if all of its lower page table entries are of the same color. Now for each region, we pick the highest level page table entry that has the same color as the region. For the address shown here, the highest page table entry with the same color as the region is at the third level here. Therefore, we shall track the access bit at this page table entry for this address. Now, consider the case if this another address was sampled over here, then the highest page table entry would be at this lowest level itself, because the level higher than that, it does not fall completely within the region boundaries. Similarly, if we pick another address for sampling, then its highest page table entry corresponding to this address will be at the second level, as we see. The telescope variant that we just saw is called the bounded variant. But sometimes a higher level page table entry may be such that, say, 95% of its covered address space corresponds to one region, but the remaining 5% falls outside it. In such a case, a telescope will be forced to profile at the next lower level of the page table, which offers less coverage. So to aid in such cases, we have another variant of telescope called the flex variant. This variant can pick a higher level page table entry to profile, even if the covered address space shoots over the region boundary, provided that the amount by which the covered address space of a page table entry shoots outside is within an error threshold, for example, 5%. Telescope flex can set different error thresholds at different levels of the page tables. This variant is called flex after flexible. Telescope's region management keeps most things unchanged from the region management scheme adopted in Damon, except for a few key modifications. If a region is profiled at its highest level by two or more page table entries in that level, then it gets split in such a way that the boundaries of the higher level page table entries are respected. After the split, the child regions will be profiled at the same level as the parent region. So in case of a merge, the same transition will occur, but in reverse. Let's look at another example of a split and merge. So if a region is tracked at by only one page table entry at its highest possible profiling level, then on a split, it gets split into smaller regions such that each of those child regions will be tracked at one level lower than the parent region. This ensures that telescopes' access tracking can get more and more precise with time if needed. Now let us look at how Telescope fares against the other state-of-the-art telemetry tools. We shall evaluate Telescope against Damon, which is, as we saw, was a tool that does region-based sampling, and against Intel's processor event-based sampling, or PEBS, that uses performance counters. We adjust the sampling interval in Damon and the sampling frequency in PEBS to create moderate and aggressive configurations. Aggressive configuration is expected to have better convergence, but with higher resource utilization. We evaluate both the flex and the bounded variant of Telescope. And in flex, the error threshold by which a profiled page table entry may shoot over a region boundary is set to 25% at the second level of the page table and 15% at the third level. Both Damon and Telescope report regions every 200 milliseconds, while in PEBS, for each sample, we consider its underlying 2 MB region as touched, and we aggregate those every 200 milliseconds. For more details about the setup, I beseech you to refer to our paper, which is part of the proceedings. Further, we are interested in two key metrics for convergence. Precision means out of all the total pages reported by a tool as hot, what percent are actually hot? Recall means out of all the actually hot pages in the workload, what percent were identified as hot by the tool? In general, higher the better for both precision and recall. We create a micro benchmark composed of 10 GB needles in a 5 terabyte address space. It is represented in this figure. This synthetic access pattern was created with MASIM, or the Memory Access Simulator. Both variants of Damon show near zero precision and recall. This is because Damon generally fails to detect any hot area when the address space is terabytes large. Both variants of PEBS show good precision because they collect actual event samples. However, the recall is quite bad because there aren't nearly enough samples to represent the actual access pattern. In contrast, both variants of Telescope offer good precision and good recall. We also evaluate Telescope on an end-to-end setup where the telemetry is used to perform memory tiering on a tiered memory system. The workload here is the Redis key value store with YCSB to generate load. The working set size is 2 terabytes. We shall monitor the Redis throughput and the tail latency of requests to quantify the impact of telemetry on the workload, and we shall also look at the amount of data migrated to DRAM to quantify the effectiveness of the telemetry. We see that both variants of Telescope outperform all other competitors in delivering higher throughput to the application. The reason can be inferred from the fact that Telescope was able to identify 30 gigabytes of hot data, which eventually got migrated. In contrast, PEBS and Damon were able to identify very little data for migration. Similarly, the 95th percentile latency of requests is lower for both variants of Telescope than the other telemetry tools. For more details about the evaluation, I request you to refer to our paper in the proceedings. So in conclusion, effectiveness of terabyte-scale telemetry, terabyte-scale tiered memory systems depend on the precise and timely identification of hot or cold data. Telescope introduces a novel page table profiling technique to quickly converge upon memory access patterns for workloads with huge memory footprints. We evaluate Telescope and compare it with other state-of-the-art telemetry techniques and demonstrate its benefits for various applications with large memory footprints. Telescope future-proofs memory access telemetry for tiered memory systems with memory capacity up to and beyond the terabyte scale. We are currently in the process of upstreaming a Telescope patch into the Linux kernel, so you can scan the QR code to see the activity on lore.kernel.org. Thank you.